So we know this. So what it means? It means that if you have a sample of size n and you calculated correlation coefficient r, first of all, you need to use these two statistics to calculate z prime and s. Okay, it's very simple. You just use the formulas that we have here. Okay. Then the next, you use normal distribution because you already know the standard deviation and you already know the center of this normal distribution at z prime. You use normal distribution to calculate z low and z up, the smallest possible z and largest possible z. Okay, and in this case, you just simply use normal distribution. So for example, if you want 95% confidence, you just take 196 standard deviations on both sides of z prime. If you want 99% confidence, then 99.7% confidence, then it will be 3 standard deviations. So you know this already, okay? And then we recalculate we use z low to get r low, and we use z up to get r up, because we know the formula that brings z and r together, okay? Or z prime and r together. But how to do that? Well, that's the formula, okay? First of all, we need to get rid of logarithm, and we know how to do it. We need just to use exponential function. So I can use exponential function to get from this formula to this one. And then just by using very simple calculations, we can calculate that r will depend on z prime using this one. So if you take z low and put it here, okay, and here, of course, you will take r low, you will get r low. And then if you do the same with z up, the largest possible z value, you will get r up. Okay, so that's the procedure for calculation of the confidence interval for the correlation. Let me show you an example. Okay, let's say we have a sample, and the sample size is, let's say, 28, just to make the calculations easier. And the correlation between x and y in our sample is 0.9. Is 0.9. Okay. So our goal is to calculate the confidence interval for rho, for the population correlation. Okay. First of all, we know that we need to compute the z prime value, which is z prime is 0.5, and you have natural logarithm of 1 plus r divided to 1 minus r. Okay. Well, we have r, it's 0.9, right? So it means that we have 0.5 times logarithm, natural logarithm, then 1 plus r, it's 1 plus 0.9, so it's 1.9, divided to 0.1, right? 0.1, which simply is 19, right? So it's 19. Then if we use a calculator and calculate the logarithm value for 19 and times 0.5, we will get approximately 1.47. 1.47. So this is our z prime value. Now the standard deviation, we know that in this case it will be 1 over n minus 3. So that's the empirically Fisher has found out. So we take 1 over square root of 25, which is 1 over 5, or 0.2. Okay. Now we calculate the confidence intervals for the z prime first, and in this case I will make my life a little bit easier. So I will take confidence level equal to 95%, because for normal distribution 95.5%, sorry, 0.5, because in this case in normal distribution I just take 2 standard deviations from both sides, right? So it means that the smallest possible value for z prime will be 147 minus 2 standard deviations, so minus 2.02, okay, which is 0.4, and 147 minus 0.4 gives me 0.107. Okay. Then the largest possible value is 147 plus 2 standard deviations, which gives me 187. So this is confidence interval. This is 95% confidence interval for z prime values. But I know that r depends on z prime, so I can use these two values to calculate the confidence interval for the rho in this case, right? We know that the r of x and y is the exponential e in power of 2z prime minus 1 divided to e in power of 2z prime plus 1. Okay, so that's what we found out. Then it means that we need to find this e in 2z prime for each cases. For the smallest case, for the lowest case, it will be e 2z prime 2 times 107, okay, which is E in 2.14, okay, which is approximately 8.5. Okay. Now for the largest possible value, we take E 2.187, right? So it's E in the power of, it will be 3.64, right? Which gives us 42.1. Okay. So these are the values for E in power 2z prime. Now I can calculate the confidence interval. So in this case, I will use rho because I calculate confidence intervals for the population. For the smallest possible rho will be 8.5 minus 1 divided to 8.5 plus 1. Okay. So it's 7.5 over 9.5. which is approximately 0.79. So this is the smallest possible correlation we expect from the population with a certain confidence level. And then the row up is 42.1 minus 1 divided to 42.1 plus 1, which is 41.1 divided to 43.1, which is approximately 0.95. Okay, so this is our confidence interval. So with 95.5% confidence, you remember I used 95.5 here, so this is also 95.5. With 95.5% confidence, the correlation between these two variables in the population should lie approximately between 0.79 and 0.95. And then you will find another example in the slides. I will not concentrate on this particular example. It's very similar to the one we had before, just the correlation is different. And then you can also see, for example, you can read all the steps from the presentation slides instead of watching the videos. Of course, when you work with real data, you will use a function that was already written and that will calculate both confidence intervals for the correlation and also make a test if your correlation is 0 or not for the population. But I wanted you to know how this function works and how actually this idea of confidence intervals works for the correlation coefficient.